The main part of what I want to do today is this geometrical representation of complex numbers. Okay, I talked a little bit about this, I think was it yesterday we talked about vectors. So we can represent complex numbers as vectors using the mod arg idea. So there's z, could be represented by the vector oz, and as we saw with vectors, the advantage of using a vector rather than a single point is I can move that vector, so I can translate it anywhere, and it retains its length, it retains its direction. If I was to move the single point, it becomes a new point and becomes a different complex number. So that's the advantage, of course, of using vectors. So yes, I could put it down there, yes, I could put it over there. It would still be representing the same complex number. And as we saw with vectors, it's just going to be head minus tail. So no matter where it is, the length, the modulus, the magnitude, call it whatever you like, and the direction, the angle, the argument, again, all just names for the same thing. And like I was saying, if we want to work out what it's representing, we simply go head minus tail. So adding and subtracting, well, we've seen it. It's really just the same as adding and subtracting vectors then. So if I have a complex number there, z1, and there's another complex number, z2, and I want to work out where z1 plus z2 is, I just slide my vector into place, head to tail, and there's z1 plus z2. And as we saw, it doesn't matter which order, I could have gone z2 plus z1 if it ends up in the same spot. And then subtraction, then we do it head to head or add the negative vector. And it turns out, when we do that, so there's the actual position of the complex number z1 minus z2. But of course I could slide that vector and it becomes the other diagonal of our parallelogram. So all those things we saw in vectors are going to become useful here. The triangular inequality is, well, it's an important little result, and it's a simple idea. If you've got a triangle, any side has to be shorter than the sum of the other two sides, because the shortest distance between any 2 points, straight line. So if I have a triangle, ABC, I can say, well, I know that AC is always going to be less than AB plus BC. But if I go up to my vector diagram and have a look at the triangle represented by Z1, Z2, and the green line Z1 plus Z2, well, the length of the vector Z1 plus Z2 must be less than the sum of the other two vectors. Also true that any side has got to be bigger than the difference of the other two sides. So AC minus AB. That's simply proven by, hey, look, all I've got to do is move AB to the left-hand side. And then I've got that any side is going to be bigger than the difference of the other two sides. So therefore, the modulus of Z1 plus Z2 must be trapped in between Z1 plus Z2, the modulus of those two, that would be the largest it could possibly be, and the smallest it could possibly be would be the difference between those moduli. And you'll notice I've gone absolute value there around the whole thing, because is Z1 bigger than Z2 or is Z2 bigger than Z1? Equality, when does that happen? Well, that's if ABC is a straight line. Because if ABC was a straight line, then AC, of course, is the same as AB plus BC. B would just be a point in the middle of A and C. Here's a very old Hsc question. 1995 it comes from. They gave us this particular diagram, and they've told us a bit of information. P and Q are representing Z and W. And they've even given us a bit of a hint there and said, oh, well, therefore, the length of PQ must be head minus tail, Z minus W, the magnitude or the modulus of that. Show that. So here's our triangle inequality. So all right, I'll join P and Q up. There it is, creating the third side of a triangle. And I say, well, all right, I know that the length of OP would be the modulus of Z. I know the length of OQ is the modulus of W. And I know the length of PQ is the modulus of Z minus W. And so then I can simply say, well, by the triangle inequality, I've got three sides of a triangle. So modulus of Z minus W must be less than modulus of Z plus modulus of W. Construct the point R representing Z plus W. And then what can be said about the quadrilateral? If we add them together, let's complete the parallelogram. So what can be said about the quadrilateral OPRQ? A parallelogram. That's the best we can do at this stage without any more information. Then they told us that the modulus of z minus w is in fact the same as the modulus of z plus w. What can be said about the complex number w divided by the complex number z? So they've told me the modulus of z minus w is equal to the modulus of z plus w. But remember, those two expressions represent the diagonals in our parallelogram. So the diagonals are equal, okay? We're now talking about a parallelogram, diagonals are equal. That now reduces the shape down to something more specific, being a rectangle. So I now know OPRQ is a rectangle. Well, if that is true, then the argument of w minus the argument of z must be 90 degrees, or pi on 2. Because if you look at your diagram, you'll see that, hang on, that is the vertex of what we now know to be a rectangle, which is 90 degrees. Well, using our rules, I can say, well, the argument of w minus the argument of z, that's the same as the argument of w divided by z. So hang on, what can be said about w over z? I know its argument is pi on 2. Well, if its argument is pi on 2, it's an imaginary number. It must lie on the imaginary axis. So I've said it's purely imaginary. Yeah, we tend to say purely imaginary rather than just simply imaginary, because there is that confusion out there about imaginary versus complex numbers. So to make sure that they know you know what you're talking about, say purely imaginary rather than just imaginary. Okay, multiplication. So we've seen that the modulus of z1 times z2 is modulus of z1 times modulus of z2. And we saw that with the arguments, we end up adding the arguments. So r cis theta 1, r2 cis theta 2, and so on. So it ends up being a rotation. And the rotation is anti-clockwise because we're adding the angles on. So the angles are getting bigger and bigger. And the length of the actual vector itself would be stretched or multiplied by whatever r2 would be. So all right, here's two vectors representing the complex number z1, and b is representing z1 times cis theta. So what that tells me is the angle between these two vectors must be theta, because I've multiplied z1 by cis theta. So I must have added the angle theta onto it. In this case, the length of the vector didn't change because I was only multiplying by cis theta, not a multiple of cis theta. So the modulus got multiplied by 1. So it stayed the same. If I was to multiply it by r cis theta, then the length of OB would be whatever r is. If it's bigger than 1, it'll be a stretch of z1. If it was less than 1, then it'd be a shrink of z1. And this important idea, remember, cis pi on 2 is I. Multiply a complex number by I, you rotate 90 degrees, or you rotate pi on 2. There it is. It becomes a really important fact in a lot of these questions. And yet again, I remind you, at any time, if you want to find out which complex number it represents, vectors are always head minus tail. So whatever's at the head minus whatever's at the tail. All right, let's have a look at this little diagram. And I think, if I remember correctly, this is a square. I just didn't write it down that this is a square. Now, I've been told D is the number 1, A's omega, or W, whatever you want to call that. And we're going to find now all the other points. So how am I going to do it? Well, I know that DC, remember I've told you that this shape is a square. So DC must be the vector DA rotated 90 degrees, because that's the angle in the square. The length of the vector hasn't changed because I'm just multiplying by I. Squares have sides that are the same length. Okay. So now I'll substitute in head minus tail. So DC is the point C, which is what I'm trying to find, and it's joined to 1, so it'll be C minus 1, and it'll be, well, DA, head, W, minus tail 1, times I. So all I've got to do now is make C the subject, and we've found out what point C is. So it'll be 1 minus I plus I times whatever omega happens to be. Okay, now let's find B. How could I find B? Well, I could say it's the point A, and I've added the vector DC. I've slid, or translated to use a proper mathematical term, I've slid DC into place and added that onto the point A. So the point A is omega C minus 1. C minus 1. Our C we just found out a value for, so I can sub that in, and now we can make B the subject, and we get whatever B is. That's one way I could have done that. I could have said B is the point C, and I've added the vector dA. That would also get me to the point B. So let's see what happens when we do it that way. Well, C we found out was 1 minus I plus I omega. And then dA, head minus tail, omega minus 1. And it's already got B the subject. So tidy that up and, oh good, we do get the same thing. But there's yet another way of getting that point. I could have said, I've got the vector dA, I have rotated it to get the vector dB. Well, if I've rotated it, it's a square. We know diagonals are at 45 degrees, so I must have rotated it 45 degrees or cis pi on 4. But the length would change. And if it's a square, then the hypotenuse of that right angled triangle that's half of the square would be in the ratio 1, 1, root 2. So I must have multiplied the length by root 2. So I could multiply the vector dA by root 2 cis pi on 4. I should get the same thing. So let's see what happens. Well, dB, the vector dB will be head minus tail, so it's B minus 1. Root 2 cis pi on 4, well, I'll expand that out so I know exactly what I'm looking at there. So cos pi on 4 plus I sine pi on 4. And that will be times dA. And again, that'll be head minus tail. So that's W minus 1. Okay, I'll move the 1 to the other side. But the other thing we know is the cos of pi on 4 is 1 on root 2. Multiply it by the root 2. We get 1. Same with the sine pi on 4. So I now have 1 plus I times omega minus 1 plus 1. Well, okay, that's all right for an answer, but let's show it is in fact the same as the other one. So if I expand the whole thing out and then group, I can see, oh yes, it is indeed the same as the other ways of getting B. There's a third way I could do that. Here's one from the 2000 HSC. We're told the shape's a rectangle and the length of OC is twice the length of OA. And A is representing omega W, call it what you will. So what complex number corresponds to C? So how do we work out C for this one? Well, they've told me it's a rectangle. So I could rotate the vector OA 90 degrees, but I'm also going to have to stretch it. We said the length was double. So it would be, the vector OC would be the vector OA times 2I. Well, the vector OC is the same as the point C because it's a position vector. It's anchored at the origin there. Same with OA. So we get C is 2I times omega. What complex number corresponds to the point of intersection D, which is the diagonals in OB and AC, where they meet? We know the diagonals in a rectangle will bisect each other. Okay. So therefore D is the midpoint of AC. It's also the midpoint of OB. But I'm not going to use OB because I don't know what B is at this stage. But I now have an expression for both A and C, so it's actually going to be quicker to work out that midpoint. I don't have to work out the third point. So I know it'll be whatever the point, it's midpoint. So I'm not using the vectors this time. I'm saying it's the midpoint of A and C. So A is omega. C we just worked out was 2I omega. All of that divided by 2. So D is the point. A half plus I omega. Okay, so what have we been told? OBA is an equilateral triangle. OBCD is a square. We have to find BDC, BD and C, and I think they're giving us a bit of a hint there. Why didn't they say find B, C and D? And sometimes the language of the question is giving you a hint in the order to find things. So it might be easier to find B, then D, then C. Okay. Well, let's find B then. Well, the vector OB I could get by rotating the vector OA, and it would be cis pi on 3. We're told that's an equilateral triangle, so it must have been rotated 60 degrees, pi on 3. And OA is just the number 1. So B is whatever the cis of pi on 3 is, well, we could actually work that one out. Pi on 3 is an exact one. So we get a half plus root 3 on 2i. Okay, there's b. How will I now get d? Well, that's a square, so now I could rotate that a further 90 degrees. So I could get my answer I just found and multiply it by I, and there we go. We get minus root 3 on 2 plus a half I. So we have d. How can we find c? Well, again, there's several ways of finding this one now. I could add the vectors OB and BC. I could add the vectors OD and DC. I could rotate OB 45 degrees and stretch it by root 2. Which way did I go with? I've just gone, okay, from the point B, I'm going to add on the vector OD. So B, we worked out, was a half plus root 3 on 2i. The vector OD was minus root 3 on 2 plus a half I. And what a lovely expression. There's the complex number that C would represent. 1 minus root 3 on 2 plus 1 plus root 3 on 2i. So, interesting diagram. For some reason, part 2 is missing. It's part 1 and part 3. Explain why P corresponds to the complex number 1 plus I Z1. So how do we get to the point P given everything else we've been told in this diagram? P, the only thing I really know about it is it's part of the vector AP. And the vector AP would be the vector AO rotated 90 degrees, but this time it's anti-clockwise I'm going. Sorry, this time it's clockwise I'm going rather than anti-clockwise, so I'm multiplying by negative I instead of positive I. So P, to avoid any confusion, the reason I've gone with minus I can do that because it's 90 degrees I'm rotating. If it was 45 degrees, then I would have to multiply by cis minus 45, not just the negative of cis 45. They are two different things. So it's actually cis of the angle. But because I'm dealing with 90 degrees, and the cos of 90 is 1 and the sine of 90 is 0, in this case I can just say, oh, it's negative I. P minus A is P minus Z1. It'll be negative I times, well, O is 0, minus Z1. Rearrange that. Oh, look. That's why P is 1 plus I times Z1. It works out nice. Let M be the midpoint of PQ. What complex number corresponds to M? I reckon that the missing part 2 was probably something like, what complex number is Q? That's probably what we need here. So let's find Q, because how am I going to find the midpoint of PQ if I don't know what Q is? So similar to the first one, QB I'm going to say is BO times I. This time I am rotating anti-clockwise. So subbing in for B. B, what do we know about B? B is Z2. So we get 1 minus I Z2. And so now we're finding the midpoint. So it'll be P plus Q on 2. Sub those two in. I mean, that's probably good enough for an answer, but well, let's make it the real part plus the imaginary part. But in a way, I haven't really made it the real part and the imaginary part, because remember, Z1 and Z2 in themselves are complex numbers anyway, so the first one probably was good enough for an answer, but there it is. Okay.